Continuing on, this is part 3, part C, that is data preprocessing for feedback analysis. This video will be quite lengthy as it covers from question number 9 to question number 18. So the first question of this video, which is question number 9, includes accuracy, completeness, consistency, and feedback. Feedback data quality is often affected by three major issues. Accuracy refers to whether the recorded data is correct. Students may accidentally enter wrong ratings or inconsistent comments. This can be improved with validation checks and controlled uh, answer formats. Completeness concerns missing ratings or skipped questions. High incompleteness weakens reliability. Techniques like reminder, prompts, compulsory fields, or imputation can address it. Consistency means the feedback should not contradict itself. For example, rating a course excellent by giving low scores for every teaching parameter. Consistency improves through standardized service design and rule based cleaning. Two additional quality dimensions include timelines, meaning is collected in right time, and uniqueness, meaning no duplicate entries. Together, these factors define how trustworthy your feedback analytics can be. Question number 10, moving on to question number 10, we have handling and missing feedback values. These are several methods to handle missing values in feedback datasets. First is ignoring tuples, which works only when missing data is very small and randomly distributed. Second is filling manually, used when human judgment is needed. For example, faculty adjusting unclear values. Third is mean, median, and or more imputation, which replaces missing values based on central tendency. This is simple but may reduce variability. Fourth is class specific imputation, where missing values are filled based on their group, like department or course section. This often gives more realistic results. Finally, most probable value imputation uses statistical or machine learning models to estimate the best possible replacement. Choosing the right method depends on amount and nature of missing data. Next is moving on to question number 11, which includes smoothing, outlier detection, and noise removal. In this question, we smooth feedback ratings, which binding with bin means. We divide the sorted ratings into bins of depth 3 and replace each value with the average of that bin. This reduces noise and small fluctuations. Next, we detect outliers, which is unusually high or low ratings. We can use the IQR method, marking values below question number 1 to 1.5x IQR or above question number 3 plus, which is 1.5x IQR, or the Z-score method, where the Z suggests an outlier. To remove noise, we apply smoothing techniques like binning, moving averages, or simply removing extreme outliers when justified. These steps make the data set clear, cleaner, more stable, and more useful for further analysis. Next, we move on to question number 12, which includes schema integration, redundant data, and conflicting values. When integrating multiple databases such as MCAT feedback or exam systems, three issues arise. Schema integration means combining tables that may use different names, formats, or structures. We use this by mapping attributes, unifying data types, and creating a common schema. Redundant data refers to duplicate entries from multiple surveys or repeated imports. This is handled through deduplication, entity resolution, and merging identical records. Conflicting data happens when the same student or course has different values across sources. Conflict resolution rules such as prioritizing the most recent values are used, and effective integration ensures all data sources work together smoothly for reliable analytics. That concludes question number 12, which was schema integration, redundant data, and conflicting values. Next is question number 13, which includes normalizing types. In this question, we compare four keys normalization methods: min-max normalization rescales values to a fixed range like 0 or 1, making all features comparable. Z-score normalization centers data using its mean and standard deviation, producing values with mean 0 and SD1. This is powerful when data contains outliers. And the mean normalization centers the data around 0 using mean and range. Next is decimal scaling, divides values by power of 10 and reduces their magnitude. Each method prepares data for algorithm differently. Choosing the right normalization depends on the model and the characteristics of your data. Next question is question number 14. Now that we have learned normalizing, now we are going to normalize 200, 300, 400, 600, and 1000. In this task, we normalize the values 200, 300, 400, 600, and 1000, as I said, using four methods. For min-max normalization, we use the formula x minus min divided by max minus minimum. With minimum equals to 200 and max is equal to 1000, each value is rescaled between 0 and 1. For z-score, we subtract the mean of the dataset and divide by standard deviation, giving standardized value. For mean normalization, we apply x minus min divided by maximum minus minimum. For decimal scaling, we find the highest absolute value, that is 100, that is 1000, and divide each value by 10, 10 by the power 3. Now, these transformations help models interpret the data on equal footing. That was normalizing the given values. And now moving on to question number 15, that is normalizing value 35. Here we normalize the value 35 using three approaches, which is for minimum minus maximum, we use the formula x minus minimum divided by maximum minus minimum, as I said, based on the given data set. For the z-score, we use the formula z is equal to x minus mean divided by standard deviation, where mean is equal to 40 and SD is equal to 12.95. 35 becomes a negative z-score, indicating it lies below the average. Now for the decimal scaling, we divide 35 until it becomes a value less than 1. This question reinforces how a single value changes depends on normalizing techniques. That was normalizing. Now we should know which normalization is best. We have learned quite a few techniques now, and the question number 6 includes the question why and which normalization is best. According to me, there is no single best normalization method. It depends entirely on the situation. Use minimum minus maximum normalization when you need values strictly between 0 and 1. such as neural networks or distance-based models. Use z-score when data contains outliers or when you want standardized values for comparison. Use decimal scaling for very large numbers where simple scaling is enough. Use mean normalization when you want values centered around zero without removing variation. The right choice depends on your algorithm and nature of the data. Now, concluding this, the next question is z-score normalization and covariance. Um, Firstly, we apply z-score normalization to productivity values. We subtract the mean of the list and divide by the standard deviation. This converts all values into standard units, making them comparable. Next, next is we compute covariance between this data set and another related variable such as time spent on output quality. Covariance tells us whether the two variables increase together, that is positive, and move oppositely, that is negative, or show no relation, that is near zero. Finally, we interpret covariance. If it's positive, better productivity is associated with higher values of second variable, indicating a positive trend. That was z-score normalization and covariance. Next and the last question of part C is equal frequency and equal width clustering. The last question is, in this question we partition data using three different strategies. Equal frequency, partition divides the data so each bin has the same number of values. This ensures balanced bins even though the data is skewed. And next is equal width partitioning. Equal width partitioning divides the entire range into equal sized intervals. This is simple but can produce empty bins when the data is uneven. Clustering based partition groups data based on similarity using algorithms like k-means. This produces natural grouping and often gives the most meaningful bins. Each method has a purpose: equal frequency for balanced data, equal width for simplicity, and clustering for smart grouping. And that was the end of part C. I'm going to see you in the next video, which concludes part D of this internal one test paper, and that will be our last video.